0.
Hi, everyone. Thanks for coming back again. This is Ken Shoulders number 49. And today we're going to be going through something pretty awesome. It's a paper from Pavel Asmira, and it is called Vortex Ring Fractal Structure of Hydrogen Atom. We've gone through a few of Pavel's papers before. This one's got something special in it. Once we get to the end, we'll talk a little bit more about it. So we have Chip reading today. Thank you, Chip. And yeah.
All right, this is from the Proceedings of the World Congress in Engineering and Computer Science 2009, Vortex Ring Fractal Structure of the Hydrogen Atom, Pavel Asmira. Abstract in highlight. This paper is an attempt to attain a new and profound model of nature's structure using a vortex ring fractal theory, VRFT. Scientists have been trying to explain some phenomena in nature that have not been explained so far. The aim of this paper is the vortex ring fractal modeling of elements in the Mendeleev's periodic table, which is not in contradiction to the known laws of nature. We would like to find some acceptable structure model of the hydrogen atom as a vortex fractal coil structure of the proton and a vortex fractal ring structure of the electron. It is known that the planetary model of hydrogen is not right. The classical quantum model is too abstract. Our imagination is that hydrogen is the levitation system of the proton and the electron. Okay. Introduction. As the model of the index terms here, the model of the hydrogen atom, vortex ring fractal structures, covalent bond. Those are key search words. Introduction. Number 1, the electrical force decreases inversely with the square of distance between charges. This relationship is called Coulomb's law. There are 2 kinds of matter, which we can call positive and negative. Like kinds repel each other, while unlike kinds attract. Unlike gravity, where only attraction occurs. When charges are moving, the electrical forces depend also on the motion of charges in a complicated way. Fractals seem to be very powerful in describing natural objects on all scales. Fractal dimension and fractal measure are crucial parameters for such description. Many natural objects have self-similarity and partial self-similarity of the whole object and its part. Fractality. All right, most of our knowledge of the electronic structure of atoms has been attained by the study of the light given out by atoms when they are excited. The light that is emitted by atoms of a given substance can be refracted or diffracted into a distinctive pattern of lines of certain frequencies and create the line spectrum of the atom.
I think that's supposed to be excited. When atoms are excited, I think that's a spelling typo. Anyway, carry on.
Yes. The careful study of line spectra began about 1880. The regularity is evident in the spectrum of the hydrogen atom. Interpretation of the spectrum of hydrogen was not achieved till 1913. In that year, the Danish physicist Niels Bohr successfully applied the quantum theory to this problem and created a model of hydrogen. Bohr also discovered a method of calculation of the energy of the stationary states of the hydrogen atom with use of Planck's constant H. Later in 1923, it was recognized that Bohr's formulation of the theory of the electronic structure of atoms it could be improved and extended. The Bohr theory did not correct values for the energy levels of the helium atom or the hydrogen molecule ion, H2 positive, or of any other atom with more than one electron or any molecule. Oops. Yeah, left out a big part.
Let me just check if there's something down here. So that's the bottom of the page, isn't it? Yeah, that's the bottom of the page. Yeah, okay.
Yeah. During the 2-year period from 1924 to 1926, The Bohr description of electron orbits and atoms was replaced by the greatly improved description of wave mechanics, which is still in use and seems to be satisfactory. The discovery of the de Broglie by de Broglie in 1924 that an electron moving with a velocity v has a wavelength lambda equals h over mev. The theory of quantum mechanics was developed in 1925 with the German physicist Werner Heisenberg. Early in 1926, an equivalent theory called wave mechanics was independently developed by Austrian physicist Erwin Schrödinger. Independently is important. Important contributions to the theory were also made by the English physicist Paul Adrian Maurice Dirac. The most probable distance of the electron from the nucleus is thus just the Bohr radius. The electron is, however, not restricted to this distance. The electron is not to be thought of as going around the nucleus, but rather as going in and out in varying directions, so as to make the electron distribution spherically symmetrical. A probability cloud, my insert. All right, matter is composed of tiny atoms. All the atoms of any elements are identical. They have the same mass and the same chemical properties. They differ from atoms of all other elements. 20th century X-ray work has shown that the diameters of atoms are in the order of 2 nanometers. The mass and positive charge are concentrated in a tiny fraction of the atom called the nucleus. The nucleus consists of protons and neutrons. Protons and neutrons are made of smaller atomic particles such as quarks. Both protons and neutrons have a mass approximately 1,840 times greater than an electron. The more energy an electron has, the further it can escape the pull of the positively charged nucleus. Given sufficient energy, an electron can jump from one shell to a higher one. When it falls back to a lower shell, it emits radiation in the form of a photon. Electrons and photons, that's all we have. They're kind of important. The spin of the electron. Part 2. It was discovered in 1925 the electron has properties corresponding to its spin s. It can be described as rotating about an axis of a ring structure of the electron. The spin of the electron is defined as angular momentum. There's an equation there for angular momentum. For the spin on axis z, we have a polarized spin, quantification there, where m is the mass of the electron, r is the radius of the electron, and n is the number of substructures inside of the structure of the electron. In the formula for the radius of the electron, we have a development there where I see 8 pi. It's a little bit of relativity in there. Going on to the next page, we have radius and velocity described. We're going to end up with a momentum description here in a minute, I think. Description for the velocity. It's v mean velocity of the electron. We have a mean radius of the electron. We put that together.
Subelectron. That's that's important.
Yes, the mean velocity of the electron. V being the mean velocity of the subelectron. And Vm is the maximum translation velocity of the electron. VME is the maximum velocity of the subelectron, which is the maximum rotational velocity of the electron. If the electron has distance, very specific distance defined, and a minimum energy, a series of equations describing the minimum radius using circular spherical cloud 8 pi and mass associated with it. Pi again.
I have a question.
Yes.
Because they introduced subelectron. Did he mention any sense of how many subelectrons are participating in making the electron? They just introduced that word, and it sounded like there's many of those participating in a structure of electrons. You see it the same way? He's modeling the electron by a lot of subelectrons.
Yeah.
Okay, we all
Um,
interpret that the same way.
and
Okay, then
and
I want to get a sense of how many.
and that, Maury, that could probably be considered the etherons, right? There is a term in here that he uses once we get to it that I'll talk about. That basically, when he's talking about subelectrons, he's talking about etherons essentially that form these toruses that are the building blocks of everything essentially, right? I don't know if he goes into how many. We'll have to dive in a little bit more to
Okay,
get that.
Oh,
you
well,
could
Paul,
think of 100, or you could think of 10 to the 23rd, right? It's hard. Just get a sense of the model. That's
Paul,
all.
in subquantum kinetics, for the number of etherons that make up a proton or a neutron, Paul gave an estimate of I think it was 10 to the 65, something like that. I don't know. Sorry, 10 to the 65 etherons per cubic centimeter. I wondered if he got that estimate for chemistry. So I wondered how he
Mm.
got. It may have been some sort of like approximation that he got from chemistry. So he said 10 to the 65 etherons per cubic centimeter. Anyway,
Interesting.
Oh, well, we're down at the nanometer. Okay. Well, whatever. But in
but
this theory here, it was not mentioned that, right? We introduced the phrase subelectrons, but no sense of their size.
Yeah,
Am I
I had
interpreting that correctly?
Yeah, yeah. And I think also to form the Turing wave, it takes about 100 billion electrons. So it's a lot of them essentially. Yeah. And there is a
I'm just
term in
saying
here again.
etherons, Eddie, etherons.
Yeah, yeah, etherons. Yeah. There is a term in here also that once we get to it, I'll point it out, that comes out of this that's really interesting. I kind of wish Pavel was here to answer some of the questions. He was with us yesterday,
You can
actually, on
always
the
ask
Saturday group.
ChatGPT or on the internet or whatever it might, because it knows about
Uh,
Pavlov's
I
work.
let's just carry on with the paper. It's quite long, and
interesting. So just to comment on my own, I had never heard that term either, Moray, subelectron. I think what Pavel is trying to do, and correct me if I'm wrong, is give a geometric structure through the toroidal concept as opposed to the probability cloud for an electron. You never know where it is, and if you do, you don't know its momentum, right? 1924, Erwin Schrödinger.
and, and
So this is an entirely different approach. We're looking at a way to
yeah.
actually apply sacred geometry, the goddamn, internal atomic structure of everything.
See, Pavel didn't know about etherons. Essentially, he didn't
Yes.
know about the subquantum kinetics part. So, but it is introduced into this paper. That's exactly why I brought this paper out to do today to
Yeah.
talk about this stuff, right? So, but there is a term, like I said, towards the end that will come out that talks more about this. So let's just carry on.
Yeah. Yeah. Well, it'll all come together, I think. So there's a series of equations describing the spin S sub Z on the Z axis. And we work our way through those.
And that's important right there, the M.
Yeah, the mass of S plus or minus being the spin, plus or
Yeah.
minus one half, right? The result in 8 is in coincidence with the generally understood equation for the spin, where M sub S is spin quantum number. We can suppose that a fractal structure of the electron has a wavelength lambda equals n lambda sub 0, 2 pi radius, blah, blah, blah. That's the diameter. From figure 1b, we'll just skim through this very quickly, where n is the number of subparts. We're trying to pick out the main parts that he's throwing into the equation. For example, the subparts could be a number of subelectrons. And continuing down, formula 7 leads to, next page, the description for S sub Z. And just parse through that very quickly. Wavelength structure with subparts n dot lambda sub 0 with velocities. It can be an explanation of de Broglie's equation for a wavelength lambda equals h over mv because we suppose that the electron energy E sub t of translational movement is the same as the rotational energy E sub r of the rotating electron.
So that's figure 1A and B.
That is precisely why the atom doesn't explode and blow itself all to hell. It's balanced. Electron. All right. Very, very interesting. Very interesting
Do you
description.
want to move on? Do you want to move on?
Diagrams.
Chip?
Yes, we'll go ahead.
Oh, you should read that. Whoa. Go back.
Back
Go
up
back
to
to
this. Yeah, the caption
Figure,
on the
figure
figures.
one. Yeah,
Yeah, the
definitely.
electron that is moving with velocity v has a wavelength. Lambda equals h over mev, de Broglie's equation. Part A, relation between lambda and lambda sub zero in the fractal ring structure of the electron is figure A. All right, that's his thesis right there.
And this B part is the important part right here.
Yes, and B is an inner ring of the electron with spin quantum number 1/2 twice around analog to match. Okay. It is the 21 multiple double helix line structure. Here, only one double helix with markers. My God.
So we're starting
amazing.
to see this same structure that Moray King talks about all the time, with it twisting on itself. But let's
Yes.
carry on, right? This is great stuff. This is a fantastic paper that Pavel sent to us.
Jeez. All right, moving on down, part 3, model of the hydrogen atom. In a new model for the hydrogen atom with a levitating electron, there is attractive force F plus and a magnetic repellent force F sub minus. All right, balances itself. The hydrogen atom can have the electron on the left side or on the right side. The attractive force F plus is Coulomb's force. The repellent force F sub minus is caused by magnetic fields of the proton and the electron. A distance between the electron and the proton is d. The electron moves as yo-yo in figure 3. All right, there's a Bohr radius description there, and moving on down, I think we'll get to figure 3 in a minute here.
So
on the next page.
And this is where it gets interesting, guys.
Holy shit.
Look what we have here, right?
So,
Yeah.
you want to go to figure 3?
Okay.
Whoopsie.
Yeah.
Sorry. Figure 3.
Yeah. Here's figure 3. Describing the displacement velocity v and rotational velocity v of the electron. Plus and minus, they appear to be balanced.
So
continuing down.
One thing that's really important to understand too is Pavel's theory is that all of these structures have a rotation in one direction and a rotation in the other direction. So there's counter rotation, and the magic happens at the null point or at the 0 point. So that's really, really important to understand in all of Pavel's work. And that's why we end up with these pluses and minuses when he talks about things. He's talking about both sides, right? One spinning one way, one spinning the other way. Yeah.
Yeah, Paul,
Excellent.
do you have anything to add to that?
Okay.
Paul Harris, are you there, Paul?
Yeah, just trying to unmute my.
Oh,
But, yeah,
I wanted to comment on the counter rotating fields. Okay.
Yeah, and wheels within wheels from the top down.
Yeah, just
All
like
the
Bob Grenier talks about, right?
Yeah.
Yeah,
that's the secret of ether physics right there. Counter rotating toroidal rings. And Christ almighty applies to virtually everything.
And this right here is actually the real secret, like this drawing here. So we should go, you can read it, but go in and we'll look at all the different things that I highlighted there too.
Yeah. So we have a description of a levitating electron, and Ed, you can jump in here. It looks like a radius. There's a mag and an electrical field defined. And the mag and electrical fields are described as pretty much balanced. The electrical field and the mag field shown in a toroid description, a classic Dan Winter dodecahedron, with a proton sitting. It is of a proton. Oh, I missed that.
Well, this is
So-
this is the hydrogen. So you've got the proton and the electron.
In the electron, yes.
And the electron is levitating. This is the most important part of this whole thing.
Right.
Yes.
At a
Yep.
distance, because I remember when Moray asked if it was levitating within the toroidal structure, but it's not. It's at that d distance, d do
Yeah.
sub o, I think it is.
D sub E or whatever it is. Yes.
Yeah,
I
yeah.
got there. And so that creates a probability cloud in and of itself, but it gives it structure. Fascinating. This is really interesting. All right. It gives it a definite structure. It isn't so ephemeral in the case of quantum field theory. Figure 4. We have some distances shown and described, diagrammed out between the protons and electrons. There's a left side orientation, a right side orientation of hydrogen molecule ion, and a hydrogen molecular H2 with a covalent bond, describing to scale, I presume, those distances relative between the electron and the proton.
Yeah, D, look at D, that's probably the most important one.
Yeah.
Because it talks about the balance, like you said, the counter rotation. Yeah.
Yeah. Between the mag and the E fields. Yeah. R sub E is shown there, the radius of the electron distance away. Wow.
And this is why we gave Pavel a Nobel Prize from the Starburst Foundation for this work exactly, right? It's brilliant. Yeah, and it lines up with all of Ken Shoulder's work and Bob Greenier's work. They're all this toroidal structure, essentially, right?
Also, Pavel was a professor of computer science, so he understands academic work and teaching and things like that.
Yeah.
Could
This is amazing.
that the figure D, if you go back down?
Yeah.
Figure D, is that in the center there, is that an A field?
And alpha.
It's in a those are two toroids.
Yeah.
I wonder if they were moved closer together, possibly further out, maybe probably closer together. That there would be an A field created there from the toroids, I mean.
Yeah. You can see that there's one on each side, but there's also the electrons that are top and bottom that are in the middle there. That he's showing, and those are the levitating. They levitate within the proton, essentially, just like it showed in the first figure 2, essentially. But as we go on, it'll describe more and more of this, what's going on here.
Yeah, scale, yeah, different scale, perhaps, yeah.
Okay. All right, so there's an equation describing the quantum model of hydrogen using the radius of the electron. Okay. See 4 pi mass velocities to see a mu, which is not sure what that is. Mu and nu both. All right, the Greek alphabet has entered the picture.
So the speed of light divided by the square or the square root of 2.
Frequency or velocity?
Velocity.
Mu is the permeability of free
velocity is there because velocity and velocity.
Right, Moray, yeah.
Okay.
C divided by the square root of 2. All right.
Okay, now this is where it gets interesting again, right? He's showing how these toroidal wheels within the wheels form themselves and what's going on with all the math, right?
Okay. Protons diameter d sub nh. There's a p sub 2, a proton radius from the center of I guess there's a toroidal centroid of sorts that shows the levitation on the outer rim of the electron.
And there's the counter spinning toroids there, yeah.
Yes, the arrow is going in 2 different directions.
Yeah.
So that's the only way it could levitate out there, right? It would have to be counter-rotating. If that got bitched up, the whole thing would collapse on itself.
And in his whole theory, everything is counter-rotating also. Yeah.
Yes.
And this is the neutron, right? So this is the the structure of the neutron. The next one is going to show the proton.
Studying classical quantum mechanics, typically to get the stabilization thing, it had to bastardize a lot of the equations.
Yeah.
And he is doing this with simple counter-rotational, which is very intuitive.
Yeah.
Simple counter-rotational effects, stabilizing everything with, embedded frequencies for literally everything.
Getting back to audio for a second, an analogy here is that turntable brand, which I may remember the name of. They have counter-rotating. Counter-rotating turntable. Yeah.
Oh, yes.
Counter-rotating platters.
Platter, yeah.
Right, Ed?
Yeah.
Yeah. And that's to cancel the inertia.
Yep, exactly.
So the chassis doesn't vibrate, disturbing the stylus, right?
Nice.
Yeah, exactly. That's a good point. Yeah, thank you.
I still have one. It's in my garage. It's a phase linear turntable.
Oh, I have
really? They used two platters, like counter-rotating?
Yes. No, it's an amazing thing. Of course, they made amplifiers too. They were solid state. They were not too bad.
I know. Yeah.
Okay. Moving on. There's a set of equations again describing in more detail this. Let's go on to section 4. Figure 6 is a little complicated. Structure of electromagnetic field. Electric lines or rays with different substructures, positron and electron substructures in parentheses, repel each other. See figure 8. The same types of substructures, lines, attract each other and create braids. The same behavior has a magnetic field. Magnetic lines or rays with electron or positron substructures repelling each other, such as in figure 9. Electric lines, going to the next page.
This is where the magic starts.
Figure 7, yes. Magic lines form from electron subparts. We'll just try to get the main gist out of this. N or positron subparts. All right, so now he's getting down in what appear to be subquantum levels with the subparts, subatomic. I think quarks are going to come in here somewhere too. Magnetic lines are formed from electron subparts and or positron subparts.
So not quarks, but etherons.
Yes, even further down. I'm surprised I skipped over the quarks here, but I think they may be completely fractalized. It doesn't need to be described in any other way. Electric lines or rays are perpendicular to magnetic lines or rays. Yeah, I hope so. The ray is a braid of lines. All right, and there's a toroid described there with a whole bunch of fractalized toroids put together into a macrotoroid, describing velocities, subelectrons, pointing out the minute granularity with velocities between them.
And sub-electron as well. Subelectron and
yes.
Yeah, exactly.
Subs, yeah, maybe subs quarks and subs are etherons.
Sub would be etherons, actually.
Yes,
yeah.
That's
And
kind of my that's my instinct on that, my gut feel on that. Vortex fractal ring structure of the electron.
Which is basically exactly what Bob Grenier has been showing us since 2020.
The fractal toroidal moment.
Yeah.
Mm-hmm.
Yeah.
Excellent. It's so much better than a probability cloud.
Of course, Pavel told us that Bob Grenier went and stayed with him and they went cross-country skiing and they know each other, right?
Yeah. Bob Grenier stayed with me and I took him to Times Square.
Right.
He wanted to see Times Square at night.
Cool.
Okay, so figure 8 is titled the structure of the electric field. And we have sketches of graviton fibers and connected with toroid rungs, it would appear. Electric fields.
Oh, they twist into each other? They're twisting into each other?
Yeah, recursively braided kind of thing. electrical fields of the toroid, fractalized toroids within showing
Grav-
rotation.
Graviton
And
fibers.
then,
Yeah, graviton fibers is interesting. That again could be something to do with etherons.
That's one of the holy grails of conventional physics, is to find the
oh,
gravity,
yes,
isn't it? Is one of the,
yes.
Mhm.
Yeah, and so some of the stuff I've got from some of my guides up there have described gravitons as related completely to quark spin. So maybe that's the sub electrons, the subs are the next down, the etherons. So okay, we have electric field, electric lines, counter-rotational electric. Everything is balanced electrically and magnetically balanced. All right, figure 9 is the structure of the mag field. Magnetic lines, again, graded, balanced, with specific parameterization for the spin. No, that's not spin.
And
Yes, it is.
that's an electron-positron pair, right? The left side
It
is the positron.
Yes.
I'm looking at the symbol.
Okay. Okay.
Yes. Okay.
Mm.
With the balance forces going in opposite directions. Okay. All right. So highlighted again after structure of the electromagnetic field, the energy E sub 0 of the quiet and free electron, which is velocity v equals 0 and a quiet, I think is misspelled, quiet mass, m sub E0, can be calculated from the kinetic energy of their subparts. Let's reread that. The energy of the quiet and free electron, which has a velocity and a quiet mass, can be calculated from the kinetic energy of their subparts. Subelectrons with velocity v sub m blah blah blah, subelectrons, subelectrons with a specific parameter for velocity, subelectrons with a specific velocity, etc., all the way up to something that's got 5 subs in it with a
One,
velocity
two,
v
three,
minus
four,
5.
five.
Yeah.
Somebody needs an exponent.
Yeah.
Mhm.
So that sub again, the smallest thing that we know of is the etheron, right? As a toroidal structure that kind of builds everything. That's probably that level that he's at. We'll have to, when Pavel's with us, we'll have to ask him more questions
It's
about
a
all of
major
this.
question. Yes.
Yeah.
It's a major question. To try to bring our ideas together in this group, the SQK group, bring it all together
Yeah.
around what he's showing here. Okay, so some interkinetic energy descriptors in an equation. E equals mc squared at the bottom. Imagine that. Okay. This result is in coincidence with the well-known Einstein law. Mass is a measure of the amount of matter in an object. The object's inertia is proportional to its mass. And Einstein showed that the mass is actually a very compact form of energy. Frozen energy. All right, figure 10 explains a particle structure of the photon and a wave behavior of the light ray, which consists from more photons arranged in the series, sequence, and string. A vortex pair is created from a bath vortex and a tornado vortex. Okay, interesting.
This is really important. Again, you can see the vortex structures and how that there's rotation and counter rotation again.
Yeah,
I
pine
wonder, I
cones
wonder,
kissing.
I wonder where Pavel got this from. Whether how much of it is his ideas, or whether he got it from some secret knowledge or whatever. Yeah. Anyway, but
We'll have to ask him that. But so what goes to the right of all this, the topology transformation, this is really important because this is how he shows that a ring structure, when it's formed into itself, it becomes a particle, but when it's broken apart, basically, it's radiation or light, right? And
Yeah.
so maybe read all the highlighted stuff.
All right, so we have a description. Zed pointed out topology transformation, breaking out into vortex pairs, one vortex pair, and then more vortex pairs as a cascade, I guess, a wave envelope. In a wave format, vortex energy structure is the entire wave envelope. Okay. Ring array structure, radiation, i.e. light, and then a ring structure, which is a particle. So it's one or the other, depending on how we measure it and look at it. Just a Werner von
Is it
Heisenberg to
ring
no
structure
end.
a particle? Is that except photon, or
No,
ET.
it is a photon,
It
I
is,
think.
yeah.
Or no, maybe you're right, except
is it?
photon and
I think
except
ring
light,
structure radiation, ring
which is
structure
light.
particle.
Well, it's the wave and particle form. This is a classic double slit experiment. He's explaining how the conundrum with a double slit experiment everybody's very familiar with. You can't determine it until you look at it. And light takes every possible path through the slits and then interferes. And so he is taking an approach where the vortex, the double recursive braided vortex rings are determining the position and the momentum of light.
Well,
He's taking a whole
it's
nother approach to explaining that double slit experiment. The ray structure, which is particles, and the ring structure was particles, and the ray structure, which is, a wave field, and collapse in the wave function.
yeah, and basically what he's saying here is there's only really these two structures, and one of them, like I said, if it's a particle, then it forms into this ring, and if it's not, it's radiation, then it is this loose. It's loose basically, and when it forms into this ring is when you have a particle, right? That's the whole part of his theory here. So this is really, really critical. This part. It's got to do with the double slit, but not really, Chip. It's actual what he's saying is this is how it works. And we
Oh,
went
yeah.
through it on Saturday. There is another paper that maybe next time we can add in there that he shared with us on Saturday that explains a little bit more about all of this as well.
Yeah, it would appear that he has, with this whole concept of the toroidal nature of this, a way to be far more deterministic when it comes to the double slit experiment. he's erasing a part of the observer effect, it would seem, and saying with his math very definitively he can say what it is a priori. Interesting. All right, quantum model of the hydrogen. To calculate a quantum model of hydrogen, we use the radius r sub b of the electron, which is derived in the equation. Let's assume that in that equation 18, on the circumference of a circle, radius r has to be n of a half wavelength. On a circumference of a circle with radius of b, there has to be a half wavelength. N is a quantum number. And then we have almost a path integral here describing in a polarized field 2 pi r sub b.
I mean, it's quite simple mathematics compared to quantum theory, and
It is. It
classical.
really is.
I mean, he's got quite simple mathematics, isn't it?
There's a lot of pies in here for good reasons. He's got ring structures, right?
Yeah.
Okay.
And
So
that's a
keep
good
going.
thing. You want to get it as simple as possible, isn't it? Okay.
Yeah.
Oh God, yes. Yeah.
Okay, so 5.
Yeah, no, this is extraordinary.
Yeah. That's why he's got the Nobel Prize from us.
This is amazing. My gosh. All right, so anyway, this equation describing V sub m, where is the maximum velocity of the electron if the electron has a specific distance d sub 0 and a specific minimum energy. It's very deterministic. Jesus, there's no probability there. Energy E sub 1 of translational movement of the electron is here. So he has an energy associated with a translation. Okay. Energy E sub r of rotation of the electron is due to a maximal symmetry in the multiple double helix structure of the electric field. Oh, DNA. Has the same size as energy E sub 1 of translational movement. All right, so let's reread that. The energy of rotation is equivalent to the translational movement with his equation. So it's balanced. Total energy E sub q of rotating and moving electron is, all right, let's get a couple more equations there. Adding translational and rotational together for total E sub q. All right, from quantum number with quantum number n equals 1. So we assume we take a, we spot it at position, and it is rationalized and characterized at quantum number equals 1, and he has that equation built out. Is the same result as Bohr obtained, but with quite different hydrogen model.
That's pretty interesting too, that it comes up
In
with the same.
conventional physics, they've only modeled the hydrogen atom. They haven't been able to model the hydrogen molecule or anything higher. They've only,
it's always been a silly planetary configuration. Everybody knows that ain't what it is. Okay, so conclusions. Did you have something, Ed?
I was just going to say that this model does show that essentially, right?
Yeah.
Yeah.
All right, conclusions. It seems that gravitational lines from graviton fibers, we saw that in the figure, are in the same axes as levitating electrons. Gravitational lines repel each other, and due to the two bodies, are attracted. Gravitational lines are braids, which are created from graviton fibers. Fibers is a metaphor. A quantum foam space that is full of graviton fibers and ring structures we would like to call a gravitonium. a gravitonium, I think, would be better. A gravitonium, or going up to the next page, shortly a gravum, to distinguish from the terms vacuum, ether, etc. A gravum as opposed to a vacuum. So he's putting gravity at the foundation of this whole circus. The gravum is a space where highly organized and lower organized is a space populated with highly organized and lower organized substructures. It means that they are in a different level of self-organizational state. Fractalized, maybe. Smaller substructures can create dark matter and dark energy.
And sorry, interrupt. This is where I was going to say, remember I had something interesting to show you.
The Osmeron.
Right?
The name Osmeron was derived from the name Osmera, of Egyptian deity with 4 pairs of gods as primary creative forces. What's that? The rents from a chaos beginning. Osmerons are very small. It explains why they have immeasurable size and mass. From the basic Osmeron substructure of electron, proton, and neutrons, from the basic Osmeron, the substructure of the electron, proton, and neutron can be created. Very important.
So, that description right there reads Etheron all the way.
Yep, through and through.
Yeah, so very interesting, right?
Yes.
It's named after him.
I was going to add that, Ed, and you know what it reminds me of? Like the wells and the gravity well and the gravity hills,
yeah,
and the subcritical and the, all that just rang a bell in my head when I saw that.
Absolutely. Yeah. It does totally relate back to what we talk about for sure.
This is something that Murray has a lot of interest in. People see this instinctively, give it different names, come at it from a slightly different angle, and in the end, it would appear to be everyone is talking about the same thing.
Exactly.
Yeah.
And then you have,
that's it.
Without good experimentation, you have a consensus for reality that you can start to work on. And this is why this is so important. Anyway, the exact analysis of real physical problems is usually quite complicated. And any particular physical situation may be too complicated to be analyzed directly by solving the differential equations. No shit. Ideas as the field lines, magnetic and electric. Ideas such as field lines or magnetic or electric are very useful for such purposes. field lines, okay? Highlighted in yellow, we think they are created from self-organized subparts of gravum. Physical understanding is a completely non-mathematical, imprecise, and inexact, but it is absolutely necessary for a physicist. It is necessary to combine an imagination with a calculation in the iteration process. I have no problems with that. Our approach is given by developing gradually the physical ideas, by starting with simple situations and going towards the more and more complicated situations. All right? But the subject of physics has been developed over the past 200 years by some very ingenious people, and it is not easy to add something new that is not in discrepancy with them. Yeah.
Yep.
The vortex model of the electron was inspired by vortex structure in the PET model, the telepathic acid, I forget what that shit is, plastic bottle experiment with one hole connector, $3 souvenir toy, Portland, Oregon, blah, blah, blah. Our connector with 2 or 3 holes and a levitating magnet levitron physical toy. The ring structure is supported by experiments, number 9 and 11 also. Now we realize that the phenomenon of chemical interaction and ultimately of life itself are to be understood in terms of electromagnetism, which can be explained by vortex ring fractal structure in different state of self-organization inside the gravum. And that different state is the anisotropy potential that differentiates the ether, creates everything.
Yeah.
This work was supported by the Czech Ministry of Education.
Yeah, that's important. Yeah.
My God.
Yeah. And the next page is totally awesome. Let's just say.
I'll just show the references briefly. References there, so people see them.
Yeah.
Yeah, Pavel's reference especially. And then there's another reference at the top that's Pavel's that's highlighted.
Yeah, going back to 2007, 2009,
Yeah.
About almost 20 years ago, he did most of this work, it would seem.
Yeah. Now this is the interesting part.
Okay, so let's just
maybe just show the whole thing first, Brendan, as a whole.
Yeah, let it sit there so the viewers can see it.
Exactly right. And what you'll see is the anti on the one side, so that's spin in one direction, spin in the other direction, right? The osmiron is there.
The osmiron, yeah, the oscillon, the osmiron, the meryon, and the headion.
Headion, yeah. There's the quantum foam. There's a lot here. There's a lot going on.
Graviton fibers, source of very small rings and fibers. All right. Anti-billion. We have atoms populated with neutrons, protons, electrons, building blocks, quarks for each of those. Ring and subanalyloid, rings and waves, magnetic lines, electric lines, quantum foam. All right. Gravitational lines. There's a whole PhD dissertation on that one page right there.
Yeah, well, exactly.
An annuloid. A solenoid is equivalent to an annuloid. Is that what he's showing here? That's interesting.
Yeah.
Yes, and that's obviously the annuloid is three-dimensional spatial. Subrings, coils, solenoid. Subrings again, ring matter particles put together in a vortex ring. He's merging everything into the vortex ring. Subrings, arrays or lines of radiation and particles. He has merged radiation and particle, the biggest headache in understanding photons and electrons, and that's the double slit experiment. Nobody can explain it, blah, blah, blah. Here he has a way to do it, which alone is fascinating.
Yeah.
Topology transformations. Yeah.
Maureen, what have we got?
I noticed he only went 5 levels deep. right? You give
Yeah.
everybody a name. Oh, well, I stop at 5.
Yeah.
Yeah.
He didn't want to say sub so much. But,
Or
once
yeah.
what he did, what he's suggesting is a recursive model, a recursive pattern.
Yes.
Yeah.
And then you could keep going if you want to.
Yeah.
In
The
fact, one of the
question
things
would,
you could, if you kept going like that, the idea is, well, what happens when I do the integration? Let's say I kept going to infinity, but it integrates up to a finite amount. And then that would be an elegant model saying, oh, the process never ceases, but when it does integrate, you integrate up to the finite values that we see. So it's you could say it's a good start in the sense that we made a recursive model, so I can build up things with vortex rings. The parts that concern me is the strength of the electric field versus the magnetic field and all these other things, because he has his positrons and he has his electrons, but they're not going to collapse into each other. And so he says, well, the magnetic field causes them to stay separate. But then you say that's a heck of a magnetic field to overcome the Coulomb attraction in this case. So it's I can sympathize with the attempts to model it, and I can also understand why people could not be able to jump on board. But it would be interesting to compare what he came up with and the thinking independently by the Russians, thinking along similar lines, trying to go take the idea of the vortex ring and keep going with it in this
Yeah.
fractal sense that Bob talks about. And it's actually hard to say, what's really going on, obviously, because of the complexity of what's being suggested here.
Yeah.
But the critical things to answer is, electric field is incredibly powerful, and so why would the magnetic field uh, overpower to maintain a separation between, let's say, electron and a positron? But standard physics has the same problem. Virtual pairs, right? Electron positron pairs come into existence and go out of existence.
Yeah.
Well, it's the same problem. Why would it come into existence?
Well, that's the
I think,
Turing wave. That's the Turing wave actually coming in and out, essentially, right? And it's the etherons that are forming that Turing wave, and then it's going from into time space or space time where we are, and then back again into time space, essentially.
And then
Right?
Paul's scale of an etheron, I'm not quite sure what the scale of that is. Is a single etheron on the order of a vacuum fluctuation, 10 to the Planck length, 10 to the minus
It's
30.
it's below
Oh,
the Planck length. It's about 2,000 times below the Planck length.
well, when we talk exponents, 10 to the minus 10 to the minus 33 centimeters, and only 2,000, right? What's an order of magnitude amongst friends?
Yeah.
so more,
The point being, okay, when he says subquantum, it's kind of think everybody stopped at the Planck length when Wheeler derived it back in the 50s,
Yeah.
because we kind of washed out the whole space-time thing. We no longer have a metric. We don't have, so anytime you talk about the classical things like distance, velocity, time, because velocity relates distance to time, all that washes out at this early, if you want to call it early, dimension of 10 to the minus 33rd. That when we have a quantum foam, your key question, why was there stability at all to give us a metric? You need a metric, which is some space and some time that's somewhat stable, so you can take a derivative, right? Change of something with something else. Change in space with change of unit space with unit time. That's a velocity. So you can't really. I don't. You can do whatever you want because it's imagination, but you'll see that you'll likely, if you want to make this quantum foam your kind of baseline, and you say, I want to honor, let's say, the Planck length at least as the foundation of the etheric particle in geometric dynamics. That's what Wheeler's derivation was. you really can't go smaller than that, because we lost the notion of what is a distance, what is time, the notion of space-time. But of course, when you make up a theory, you can put whatever postulates you want, right? And see where it goes. So it's a little bit confusing when Paul postulates his etheron is smaller than the Planck length, right? Then that seems to be a contradiction right there, because we no longer have space nor time in existence.
Well, it's the etheron that forms the Turing wave, though. That is the building block, the main building block of our universe, essentially, right? So it takes about 100 billion etherons to form this Turing wave in space-time, and they're a particle or because he talks about particles and virtual particles. The virtual particle part is in time-space, so
Right. So
it
He's shown limitations in quantum theory, and he showed how subquantum kinetics can make up for the incompleteness of quantum theory. Like
I
even
understand this. Right. My question is to do with the size of his fundamental particle. When he's rather than being above the Planck length, he's under it, and therefore he's trying to make structure. That is right away. We have a contradiction right there.
Well, that's why it's called subquantum kinetics, right? Is because it's below the Planck length, and it's kinetics because it's a Turing wave that's moving.
Right.
Anyway,
Or
you make a point. You make a good point.
You have 20 orders of magnitude there between all that, what's going on at the quantum foam and electron, with no structure, no attempt at all by physics to model underneath, let's say, the electron size, classical electron
you can't
size.
see etherons because we'll never be able to detect etherons because they're too small. But you can
infer.
But
you can postulate. Yeah, you can postulate whatever you want as a postulate, right? And
what about the Compton wavelength? Is that a similar scale to the theory also?
That essentially.
Huge.
Yeah, but
you make a good point, Maury. I mean, the Planck length has been studied by conventional quantum physicists for a long time, and they've kind of like But as you're saying, Chip, a lot of quantum equations are bastardized. It's just Paul said quantum mechanics has a flaw in it, but it's workable. They can work it. Like a mobile phone has billions of transistors in it that use quantum tunneling, so they can work the quantum mechanics. It's just not there's other physics beside. It's not everything that there's other physics beside it.
Yeah. Well, one comment I had is, one of the beauties I see of using this vortex concept is that it kind of answers maybe Moray's question: how can electrostatic and magnetic fields be stable? Well, the vortex ring, I think, clearly implies an electromagnetic field. The vortex ring cannot hold itself together in an electrostatic field. The magnetic field is by definition incorporated in it. And whether it's braiding at terahertz frequencies and reciprocating at terahertz frequencies doesn't seem to matter. That one of the beauties is magnetic field's always at right angles, but to create, I think Greenier's talked about this, to create a stable four-dimensional, at least linear time, let's not talk about three-dimensional time at the moment, the electric and magnetic fields have to be completely integrated so that the vector potential field is zero. There's no alpha field. And I think iPad was talking about that a minute ago.
So
it's the monopole.
He seems to has concentrated a lot of these seemingly loose factors in quantum theory and built it all into a sacred geometry. Okay, well, sacred geometry is kind of a cop-out too. But goddamn, these little things seem to be at the heart of everything and provide incipient stability, inherent systemic stability in and of themselves between the electrical and magnetic fields.
Yeah, but also because of counter rotation, though.
Yes, of course.
Always have to go back to that.
What was Moray saying about the Planck length? The Planck length? What were you saying about the Planck length?
Well, the Planck length, was derived by Wheeler right? He called it the already unified field theory, and people said that's so complicated we can't deal with that. But all he did was he says, okay, we have the foundation of quantum electrodynamics was the energy density of the ether or the vacuum was proportional to the frequency cubed, and it would be a cubic graph, just like a cube going up to infinity. Well, obviously, if, and that's energy density, meaning it's all concentrated in there. He says, and that was that cubic equation was the starting point because that's what made the quantum electrodynamics work in their all the things they're doing in the equations of quantum electrodynamics. And so he says, well, what happens if I just, let's say, for instance, accept general relativity? He loved general relativity because he wrote the book on it, right? He loved it. So what happens?
There's
Just
the problem.
when the energy density goes to infinity. Well, nothing really goes to infinity. We know what happens as engineers. It shows an inadequacy of the modeling, so to speak. But here we have an equation that appears to go infinity. So he said, okay, if you apply general relativity to it, it pinches off. That's all. It just pinches off space-time, just like applying Einstein's equations. And he invented the word wormhole and pinches off basically towards a black hole, which is a singularity,
That's
is what they
yeah.
call it. It's an engineer is more comfortable. They don't expect models to be perfect. So they just say, fine, we hit the limit of the model. Right. Obviously, we're not modeling down there with this crude mathematics or simple mathematics. And so all he did was derive the picture in geometric dynamics. This is what happens. So here's the nature of the ether. What was basically modeled as the quantum foam whose quote particle constituent of electric flux entering, electric flux leaving was pinched off as a wormhole in the original derivation. That's where he derived 10 to the minus 33rd. And it's a foam, it's turbulence. And then you have the question is, how in the world do you get a stable metric, stable space time? Because we washed it out, so to speak. And he says, well, that's a good question, right? How was it in the average, when you get to a bigger scale, why did it settle out to look like a zero, look like a stable vacuum? So these were the vacuum fluctuations spilling into our space and exiting our space. Well, the derivation just was the orthogonal flux model.
Yeah.
Our three-dimensional space is like the plane. The vacuum energy's flux comes through at right angles,
Yeah.
right? And then a little bit of jitter as it comes through, right? If it came through perfectly, we would be detecting nothing. But there's a little bit of a jitter where it pinches off, and a little bit of energy seen as fluctuations in the metric. And that's from this flux that didn't come through perfectly straight. And he says, well, it can't be perfect because you don't have a plane, you don't have the metric, is what they call it, to even do derivatives, which means a change of delta x over delta t. There are pieces of space and pieces of time to even do a calculation. If you don't have a metric, which is space-time, you can't have any equations in terms of derivatives of space-time if that doesn't exist. So we know that everything's kind of an approximation. We do have a stable space-time because that's what we observe. So we have to explain how it stabilizes out. And so you just assume it does at the large scale because otherwise nothing exists, right? And we can't do any modeling in our three-dimensional space, etc. And so so we have a ton of modeling at the 33 orders of magnitude, 10 to the minus 33, right? And the electrons were at 10 to the minus 15, approximate, right? We have a ton of modeling that can be done in the quantum foam to make structure. Right, so you could say the Planck particle itself would be Wheeler's equivalent of an etheron, right? A little flux enters and the Planck length particle of entry, what he called mini holes in his book Geometric Dynamics. So there's his fundamental particle. This is Wheeler's, right? He just derived it, says this is pretty crude. Other people do other cutoffs. That's his general relativity cutoff. So that was Wheeler's thing. And he derived it, I think, 57, PhysRev paper. He says, well, this interesting perspective of space. Now, what can you do with it? You can't do much in the turbulence of all of that until later when we derived in systems theory and self-organization ideas from turbulence comes self-organization, and Paul jumped on that, and I jumped on it too, because that was the basis of even posing the question, tapping the 0 point energy. Why can't it be done? Because it's random, chaotic. You can't go to self-organization from chaos. And then Prigogine wins the Nobel Prize with 77, showing how it can. And then I could justify my thesis, PhD there. See, I have standard science to justify you have self-organization. And then I can point to, well, look at electron-positron pairs coming into existence, right? That's self-organization. So rather than say, oh, it's just a fictional thing, it doesn't really happen, say, no, you can say it really happens because we have the foundation of self-organization is allowed to occur. And then it happens in all sorts of scales. And then Shoulders' work has a pretty big scale, a micron self-organization that looks like a macroscopic charge. And
Yeah.
you're off and running. You have a ton of substrate, this quantum foam, to build whatever you want in your theories. Right.
When,
So I don't think it's really necessary to go down underneath of that. You have plenty if you let the
well,
Planck. Anyway,
what,
I
what,
don't know what Paul said. Did he try to
what,
dive under the Planck length? That's a
let,
question.
let me just repeat what I said to Chris Beskar one day. I said that I think that an etheron, an electron, or a charge cluster is what I said, and ball lightning are all one and the same and a fractal of each other. And he said, yeah, I agree with that.
I do
So
too.
he agrees with going below it as well, too.
Well, below the
Yeah,
Planck length.
Yes.
Well,
see
that I don't.
you can't see etheron. You can never, just like you can't see electrons or photons, but you can infer that through particle physics detectors. You can infer their existence. You can't see etherons. You can't see quarks, or not. I mean, people have a thing about quarks, but so you can infer their existence. And if you postulate their existence, then on the, so that's a subquantum level. Then on the quantum level, you get the soliton particle, a neutron or a proton or electron. And then you are coming into breaking the laws of thermodynamics in some cases. So in conventional physics, you can't break the laws of thermodynamics. The laws of thermodynamics are sacred. It's a sacred cow. You can't break the laws of
Well,
thermodynamics in conventional physics.
Prigogine extended them, and people.
Yeah. So Paul got. I mean, did Prigogine? Did he contribute to the
Paul
postulator?
Well, they
Diffusion. So
they
you
allowed it
so
because
so you can, with subquantum kinetics, the laws of thermodynamics are there. Yes, they exist, but under certain circumstances, they can be broken. So you can get.
Well,
Yeah,
Paul loved Prigogine's work. That really got him launched. Go ahead.
I think Alan had something to say.
Prigogine. I was trying to say that Prigogine won the Nobel for chemistry.
Yeah,
not physics.
77 and chemistry, because they didn't have one for systems engineering.
Subquantum kinetics is mainly based so that etherons behave like reaction diffusion of molecules. They're like tiny molecules.
Well, I understand. Now, the question I had was everybody seems sure that the etheron is 2,000 times smaller than the Planck length. Here's my homework assignment. Look it up in Paul's work. Paul postulates his etheron, his smallest thing. What did he actually say the size is, as opposed to?
He says regardless of their structure. Let me just get up the book. Let me just get up the book a minute.
10 to the negative 13.
You don't need to know the structure of etherons.
What did you say, Chris?
It would have to be smaller than 10 to the negative 13. And then when I looked into it, it was like a comparison to the Compton wavelength, in a way, if I remember correctly.
Yeah, that's quite large compared to a vacuum fluctuation, which is 10 to the minus 33 centimeters or 10 to the minus 35 meters.
Well, it has to be smaller. So, it's just like can't be bigger than 10 to the negative 13 is all I know. Or the extent
well, I'll say it right here. He wrote the book. He has his postulates. He
But it,
postulated the etheron is the basic particle impulse theory. So what is the size of the etheron? That's the question.
So that so no attempt is made in subquantum kinetics to characterize the structural nature of individual etheron entities. Regardless of their internal structure, we need only know that they are elements that compose the heterogeneous ether, that they have the freedom to move through space, and that they can transform from one type into another by following specific reaction pathways. He was saying in one of his, I think he said somewhere here that it's around about 10 to the 65 etherons per cubic centimeter. That's a
Well,
kind of guess. He said he also said subquantum kinetics is a work in progress, so it hasn't been
Mhm.
fully developed yet. It's still
And
work.
he
We're still
encouraged
research
us to play with it to figure out more also.
and looking at the Brusselator, looking at
well,
different Brusselator models, whatever. Okay, let's go down there.
Like I was saying, it takes about 100 billion etherons to form the Turing wave down at that level. So
When
we can
we don't model, when we model the
we
solid wave, we don't model trillions of, Paul said, even trillions of etherons make up a
right.
neutron. So we don't model
Now,
trillions of etherons. We just use
and
an
I didn't get a
arbitrary
sense
values.
the
there
other
from
the
what you
other
shared. I didn't get a sense of the size. I heard Chris mention something on the order of a Compton wavelength. You said 10 to
The
the
Compton wavelength, that's
65 per cubic centimeter.
Compton wavelength is for the neutron. The neutron, it's
Uh,
not to do with the size of the etherons.
right, right. It's way bigger. So what I didn't catch the size. What he said. You mentioned 10 to the 65 per cubic centimeter.
Yeah.
But I didn't see that in the book when you showed
Okay,
me
so
the book.
I'll look it up. Hang on a minute. So let's go for the I'll just put per.
you should be looking at the Turing wave because it
There's also
describes
a paper
how
that Paul wrote, The Cosmic Ether. It might be in there. I haven't read it in a while, but I have to reread that one, which I'll probably do later because now that Maury said a homework assignment, I'm going to try and figure it out.
Yeah, it's Paul.
yeah.
Paul postulated he has to give a sense of what size he has in mind. I'm sure he says it somewhere.
Did
I
he
seem to.
talk
I think
about
that this is.
fractalization of etherons anywhere that anybody knows of?
Well, that's the part where we've kind of moved it on and realized, and we actually used Ryan Wood's UFO AI to do this.
Yeah.
We realized that the etheron is the same toroidal structure that the electron is, and then of course Pavel comes along and says, well, protons and neutrons are also made up of these same exact
No,
structures,
I
essentially,
didn't
right?
realize it wasn't
But if
shared.
you
Sorry.
but if you look up the Turing wave, Brendan, that's where the description of the size and
Okay,
how it
it's there.
functions is.
That's the.
So wait, actually, Brendan, doesn't that mean it would have to be even smaller than 10 to the 65?
Yeah.
Well,
So he says, for example, 1 cubic centimeter would contain well over 10 to the 65 etherons.
All right, now we got our answer.
Yeah.
And
If we
he
put
might
it,
have a reference. There might be a reference here somewhere for how he got that.
So we could do the math to figure out, how big that is, essentially, right?
so it is 10 to the 65, and then if you look at the Planck length, that was 10 to the minus 33. So therefore, you invert that, that would only be 10 to the, and he said centimeters, 10 to the 33. So he's well below the Planck length by huge number of orders of magnitude.
Yeah.
Way below
I
the Planck
I,
length.
I thought it was 2000, but that was just something that we'd have to put it on paper. Maybe next time we'll do that. I'll calculate that out.
Also, he
Okay.
talked about how Feynman was trying to look at let's look up Feynman because that's quite interesting. And also he
30
talks
orders
to
of
Broglie.
magnitude.
So how many orders, Murray?
Well, that's 65 and 33, right?
Yeah, so about 30 orders, yeah.
30, 32.
And what I wanted to say, though, what's really important is we know that it's, I think, 10 to the 11th electrons form the charge cluster. Is that correct? From Ken
Yeah.
Shoulders? Well,
Yeah.
that is about the same thing as how many etherons it takes to form the Turing wave. So we have some fractality moving up the scale again here. And that's something that I noticed when I started looking at all this.
Yeah.
Yeah.
So sub-Planck length. Now, did Paul ever talk about that being sub-Planck lengths? Did he make the comparison in his talking? Because that's highly significant. Where you have standard physics saying we washed out space-time, and now he makes structure, which requires space-time to make structure, 30 orders of magnitude below that.
Mhm.
So that then Paul should mention that. Okay, how are we going to? There's a discrepancy. How do I have a space-time in existence when the rest of physics washed it out at the Planck length? And then even come close to going to these tiny distances, everybody gives up well before
Yeah.
they
Yeah,
even
exactly.
approach that, right? They're staying at the order of, okay, electrons, and we don't go any small sub distances below that at all in physics.
Well,
And so go ahead. What's your
Yeah.
first name, by the way?
I agree with
Alan.
Ed.
What was your last name?
Alan?
Alan, yeah. Road.
Say your last name again.
Road, Rohde.
R.
Yeah, I'm sorry, I gotta fix that and get rid of the iPad. Put my name there.
Right, because you look
I've been meaning
familiar,
to do that.
Right,
you don't look like an iPad.
Yeah, I know.
You look familiar from the psychotronics conference, but I can't remember. I don't remember talking to you. We ever engaged one-on-one at the psychotronics conference talking about stuff?
Oh yeah, I'm sure we have. I've been there since 1986, so I'm sure we have. But
Wow.
I probably wired. You probably know me best because I wired you up probably with a microphone because me and Al, the other Al, I'm one of the two Als, right? When was the last time you were there at the USPA?
Well, that's 1986 was Vern Wolf. I think I invited him to come. So the last, I think I got too busy with conferences as we entered the 90s, and I stopped going to psychotronics because now the other conferences would accept me. And so I got busy in the 90s, right, with the number of energy conferences. So we had the Tesla conference and Extraordinary Science, Steve Ellsworth.
Yes.
Start that. And then the 90s was the heyday. There were sponsor conferences in Denver, things like that. And,
yeah.
And so I have a day job, and so I could only go to so many, and they would invite me to speak. So I had to pick and choose. And so I enjoyed the psychotronics conference. I have fond memories of that.
Yeah. Well, yeah. Come on, we last year we had one. This past year we had one. We had an anniversary one.
Oh wow!
And 50th, I believe it was. And
wow.
And so we had one. The previous years we just went online, but this year we decided to bring everybody together again. So it was fun, and we might do it again this year. So I'll let you know.
Cool. Yeah, I went to my first one was number 1976. Didn't even know I was going to it at all. Chris Bird grabs me, says, "I want you to rubber hose this guy, see if he's for real." Dave Faust and me, he took us over there, and he wanted us to hear Jerry Gallimore, right?
Yeah,
right. Jerry. And so we did that, and I sat through a number of the other talks, and I was thinking to myself in this audience, dang, what a bunch of kooks. Yeah. And little did I know, a few years later, I'd be joining them. With enthusiasm, right?
Right. I know. I felt the same.
So I went to number 2.
We're still recording, by the way, so just let you know.
Yeah, it's good.
Okay, I thought I'd show you this because this is very interesting. Paul actually discovered this after he developed subquantum kinetics. So he said in their book, the Feynman Lectures on Physics, Feynman, Layton, and Sands comment on the infinite energy absurdity of classical electrostatics. and suggests that it could be eliminated by postulating the existence of an underlying reaction diffusion medium. They discussed the example of neutrons being generated in the core of a nuclear reactor as neutrons, because Feynman was working on that in the 1940s. As the neutrons diffuse radially outward through the reactor's surrounding graphite medium, they produce an inverse square flux field that has precisely the same mathematical properties as the electrostatic force field around a charged particle. Feynman et al. Speculate that the electrostatic equations of physics may just be simplified macroscopic descriptions of the collective behavior of a hidden microscopic world engaging in such reaction and diffusion processes. They ask, could it be that the real, this is from the Feynman lectures, this bit here is from the Feynman lectures. So they ask, could it be that the real world consists of little exons which can be seen only at very tiny distances, and that in our measurements we are always observing on, because they use the Feynman Maxwell's equations, they try to convert them into quantum. Maxwell's equations are based on experiment, not first principles of mathematics. They're derived from experiment. Could it be that the real world consists of little exons which can be seen only at very tiny distances, and that in our measurements we are always observing on such a large scale that we can't see these little exons, and that is why we get differential equations? Our currently most complete theory of electrodynamics does indeed have its difficulties at very short distances, so it is possible in principle that these equations are smoothed out versions of something. They appear to be correct at distances down to 10 to the minus 14 centimeters, but then they begin to look wrong. Is it possible that there is some yet undiscovered underlying machinery, and that the details of an underlying complexity are hidden in the smooth-looking equations, as is so in the smooth diffusion of neutrons? Because Feynman was studying the diffusion of neutrons in a nuclear reactor in the 1940s. But no one has yet formulated a successful theory that works that way. No one yet has made a theory of electricity for which del squared phi equals minus the charge density over permittivity of free space is understood as a smoothed out approximation to a mechanism underneath, and which does not lead. So that's one of the main forms of equation of electrostatics. That's part of Maxwell's equations, and which does not lead ultimately to some kind of absurdity. But it must be added, it is also true that the assumption that this equation of electrostatics from Maxwell's equations is valid for all distances. No, so it must be added. So it is also true that the assumption that this equation of electrostatics is valid for all distances, no matter how small, leads to absurdities of its own. The electrical energy of an electron is infinite. Absurdities from which no one yet knows an escape. So this is Paul Lovelet speaking. Feynman's speculation about the electric field being similar to the concentration of neutrons around a nuclear reactor appears to draw from his own experience from around 1942 of measuring neutrons in and around the core of one of the world's first nuclear reactors. While he was working at Los Alamos on the Manhattan Project, he had been assigned to calculate neutron equations for the Los Alamos water boiler, a small nuclear reactor at the Desert Lab. That was 10 years before Turing had published his seminal 1952 paper on the chemical basis of morphogenesis, and around 25 years before the time when the Brussels group had first published computer simulations of the Brussellator. So the idea of reaction diffusion systems and their ability to form spatial patterns was not commonly known at the time. I would suggest that the successful theory that Feynman was alluding to, that no one has yet formulated, is the present Model G subquantum kinetics theory that was published 43 years later. The little exons which he suggested comprise an as yet undiscovered underlying machinery, would be the etherons described here, whose activity produces the observable fields. Had he known about the brucillator and its ability to generate localized dissipative structures, he may have proposed that a more serious effort be made to investigate reaction fusion analogues to physical phenomena.
Yeah, and we also know that Feynman wrote a letter to Ken Shoulders, basically apologizing twice in the letter for not listening to Ken Shoulders about charge clusters, right? So, yeah, interesting.
Because Ken had the experiment, and therefore you have your observation that something's happening. And Feynman was trying to model it as the vocabulary misleads you, charge cluster. Ken didn't say that. Other people said that. He said this is more like a macroscopic charge. I made something out of the ether or whatever that appears to be a stable thing. And that's the biggest clue, especially when he made the positive ones, because they were not comprised of positrons. He never got the gamma radiation when it hit a target and dissipated. And so therefore we have structure actually created from the ether.
Yeah.
Right? And that's probably the best experiment, because Ken was showing this macroscopic structure, and he was not ready to jump on board on the vortex ring. That was popular coming out of Winston Bostick's works, the plasmoids.
Yeah.
That was just the first order perspective of what it could be, just as a first order model. Can there be more structure underneath of it? Well, first things first, let's see if we can even approximate, based on that, and then we'll worry about more substructure later, which is actually happening now from all the ideas we've just been discussing. But to postulate now that 32 orders of magnitude under the Planck length, well, I guess you can never prove them wrong. There's nothing you can postulate what you want, but
you can't.
there's a lot to learn at the higher levels that Shoulders is showing. Oh my gosh, we got self-organization occurring. Why? It's clearly not a collection of particles. And I think it was poor Hal Fox liked the charge clusters, so he wrote that a lot. But that was the wrong nickname, in my opinion, and Shoulders agreed.
Yeah.
He said a macroscopic charge of some sort. It's charge construction from the ether.
And speaking of which, I just had a flash on my thing. John Hutchison has been doing a bunch of experiments lately, and you guys should check some of the stuff out, because he's had stuff flying in the air. There's a round file, I'd like to buy it from them, that's bent in a nice curve, things that are broken. He's doing his thing again, basically. But it just flashed across my screen when we were just talking about Ken Shoulders, that John had another thing to look at, something else that he did in the last few days, because this is just in the last week or so, right? Basically. So yeah, it's cool.
So Ed, where can we find this?
Hutchison Effect, YouTube. Yeah.
Okay.
YouTube
Go to my channel, and which is called Technology Envoy. And on there's a playlist. There's a whole bunch of playlists, but there's a playlist about John Hutchison and all of the really interesting stuff. Cause he's got tons and tons of them, right? But the really interesting ones I've been putting on there. So
is Technology Envoy YouTube?
Yeah, actually, I think Brandon is about to take us there.
Oh, he's gonna. Okay, great.
Yeah.
By the way, I wanted to say, Ed, I agree with you that the fractal issue is the key here, and it's fractal harmonics or transcend all of these scale issues that we've been talking about.
Yeah, I would agree with that.
Say, Ed, I need to leave for another meeting. I'll try to get back as soon as I can.
Okay, cool. Thanks for reading for us again.
Very good.
Yeah. See you, Chip.
Yeah. And what were we just talking about? Well, actually, play the very first one, because this actually has a lot to do with with.
I'll do it on my desktop. I haven't got
Yeah,
volume on my laptop. I'll do it on my laptop rather. Sorry.
yeah.
Uh,
This is cool because apparently you have this amplifier.
Hmm.
What kind of tubes does it
Well,
use in the output? Before we
six L6s.
really, so it's
Mhm.
that's a tetrode. It's not
It's a beam.
pen-
Yeah, it's a beam tetrode.
Yeah, exactly. Some call it a pentode, but it's not really.
Right.
Yeah.
so
Um.
just before I play that, I was going to say something about what we're talking about scales and Moray King talking about that. So Paul was also saying that in the laboratory you can't see violations of the conservation of energy or thermodynamics, conservation of energy, first law of thermodynamics in the laboratory, but because it's too small. But he says, but if you go to the astronomical scale with genic energy, then you can see it much more clearly. And that's why I
Yeah.
think reasons he went into astronomy quite a lot. Anyway,
I think it's important to say and repeat this that Paul was a quantum physicist that wondered what the quantum was made up of, and that's why we ended up with the subquantum kinetics. But he was also an astrophysicist, and it's just like Brendan said, a lot of the predictions that come out of subquantum kinetics, in actually 15 of them that come out of subquantum kinetics have to do with astrophysics. So there's a connection at both ends of the scale here. But what we're about to watch is very interesting because I never thought that I'd meet the man that actually has this amplifier.
With the gain horn feed,
can you hear it?
as the gain horn would send it.
Yes.
Yeah, I can hear
I
it.
think that's the wrong one, though, Brendan.
The omnidirectional antenna.
Which one did you want?
Is that
The very
is that
first, yeah, that one. Sorry,
This
it
one?
was, I showed you the wrong one. Yeah, it's that one. Because you have this.
At that conference, and what he worked on was he called a mind amplifier, and he could play music that was recorded like through the sound system, and you would experience the emotions of the people who recorded the music.
Oh, wow.
He was able to access the feelings that were actually being. So let's say you put on Sergeant Pepper's and you listen to it, and you would be feeling what the musicians felt as they played it. It was that an intensive an experience.
Wow.
And by
that was a
extension,
special amplifier.
Yeah.
well,
Do
by
you know
extension,
much
well, it's a
more
whole
about
system.
it? Do you know how it
I
worked?
know
Or?
where it is. Yeah.
It's
I
a
know
whole.
who has it, and yeah, we've been talking about recreating it. So I'll
It's
have
a whole.
Here you are.
yeah, Alan.
It's a whole system, you know.
Has it, and
Yeah.
I think we'll get him on here because he could fill in a lot of these pieces of the stories.
That would be
But
awesome.
So has Preston
Yeah,
passed
so
away?
Oh yeah,
yeah,
he passed away in 2018, October 5th, I
Okay.
think it was.
Tell us more about the amplifier because you're saying it's a whole system.
Well, the transducers, yeah.
What kind of transducers?
It's a feed forward circuit whereby the receiving transducers in the rear, you've got four, and you sit in the crosshairs of the four diagonally.
Okay.
So the opposing rear transducer was a layout of headphone transducers.
Oh, wow.
Preston laid them out in the pattern of the tree of life because he thought that would filter out negative vibes, right?
Wow. That's interesting.
But he also had a white noise source that was mixed in to the signal that was reaching those speakers from the front. Those little transducers in the back were received. They were used as microphones, basically.
Wow. Because I know that white noise, there was a 100,000 watt white noise amplifier at Montauk.
yeah,
That was part of everything. So that's very interesting
Right.
that you say that. Wow.
yeah.
And then that signal would be mixed in a feed forward loop to the front speaker, and that would build this field, so-called etheric field, build it up, and you would sense the universe. Preston insisted that when you made a recording, the whole universe was recorded at that time, including everything. The nearest thing being the emotions or the etheric content, information content of the musicians mostly, but also the recording engineers too, anybody who was involved with it, and including you, because now you're being introduced into that field and mixed in with it, and hence you had greater appreciation of the experience of listening music on Preston's system.
Wow. And so
and I can
was
tell
it
you, I tell you a little incredible thing that happened to me in Preston's living room years ago.
yeah.
He sat me and my friend down one at a time, and we both did this. He said he played some. Honestly, I forgot the song. Just can't remember the song, but it was like a 70s classic rock type of anthem type song, but it had a lot of tracks in it. And he said, pick a track, an instrument, whatever, and then direct it with your mind. Tell it to do whatever you want it to do.
Oh.
So I chose a track, a strumming guitar track. And as soon as I selected it in my mind, it jumped over from the left channel into the middle.
Oh, wow.
Yeah. And then then when I contemplated what was happening, it went back, which says a lot,
Yeah, you're controlling it.
Yeah.
There's
so you're
connection.
part of the whole situation consciously or consciousnessly, right?
Wow. A forward feedback loop, is that
Well, I call it a feed forward because it's not a negative feedback; it's a positive feedback. It's building up.
Yeah, exactly. And we know that negative feedback actually isn't good in sound, like single-ended amplifiers. So that's really interesting to me that you're using a forward feedback loop to create all this. What other output tubes did it have? Was it a push-pull amplifier? It must be.
Push-pull. It had 6 CL6 driver tubes.
6
and conventional, line, input tubes.
Yeah. Wow. I'd love to see it sometime. Maybe we can have a look
It's not
at
much
it.
to look at. It's basically a modified Fisher 100.
Oh.
Mono amps.
Oh, and they're monoblocks too. Oh my God. That's even more exciting for me. I love monoblocks.
Okay. All right.
Separate power supplies and everything, right? But I think that might be really important with what Preston is trying to do here, because if it's got to do with right and left, the power supply can be a problematic thing because it's connected to both sides. So that's maybe why he chose monoblocks also.
So where are you located at?
Dawson Creek, British Columbia, right at the beginning of the Alaska Highway, basically.
Eddie,
Up
what's
there.
the main thing about Eddie?
Way
What's the
up
main
there.
thing about Preston Nichols? What's the important thing about Preston Nichols?
The important thing about him?
Oh,
He
wow.
was the engineer
Everything.
on the Montauk project. He worked on all the
right.
yeah.
Montauk.
Yeah, he was the focal point of the Montauk project. If
Montauk,
you've heard of it.
is that the time traveling jets?
Yeah, the experiment.
Yeah. Like we went through it the last couple of weeks, basically. We've been talking about Montauk.
Yeah.
And so, yeah, time traveling, definitely. And again, my friend Rebecca Rose, she sat in that chair many
God.
times. Yeah, she's a secret space program girl. And she also does Akashic readings, if you know what those are. Really, she's amazing. I've been
Where is
trying
she
to get
located?
her. She's up in Alaska. She's at the. I'm at the beginning of the Alaska Highway, and
Everybody
she's at
I know is up
other
in the
end.
Pacific Northwest.
Yeah, exactly right. And you're in New York?
I'm in Midtown Manhattan.
Yeah, wow.
And we're getting inundated with snow, man. I'm afraid to look outside.
Oh yeah.
I heard about that actually. I have a friend who also
I'm in Long
lives.
Island.
Yeah.
Oh, you're in
guys
Long
are-
Island? Are you
guys
getting
are-
anything out there?
Yeah, oh my God, we got like half a foot already. That's why I had to run out because the dog, he won't go in the snow too far, so I have to go out with him to get him to go on the grass.
Yeah. I
But
have a
he's a
friend.
puppy, so he's like, "What is all this?"
I have a friend who lives in New York City as well too. You might know her. She's the co-host of the Gutfeld show. Her name is Kat Timpf, and I get
the
to spend.
Gutfeld show. What a great show.
Yeah, and so she's on there, and I get to spend like every week about an hour with her to hang out and do a live chat and whatnot. There's about 20 or 30 of us that hang out with her.
I'll be happy to show up to that.
Oh, well, that could be arranged, actually. Yeah, she's really, and she's funny too, right? 'Cause she's a stand-up comedian and all that kind of
Oh
jazz.
God, I love it when people make me laugh. So
Yeah, well, watch the Gutfeld show. So on my channel, there's actually it's kind of a funny story because she knows about Stavati Aerospace and all of the stuff about Stavati, and Donald Trump ended up on the show. And Kat actually asked about Area 51, asking Trump about if there were aliens there. So I did a short clip and I've got it on my channel. And just a couple days ago, it went over 100,000 views, which is for me is phenomenal because I only get a few hundred at most, right? So that's on my channel as well on Technology Envoy. But there is something else. Brendan, could you go back to my channel? I want to show these guys one more thing that is really, really important. And these are interviews I've interviewed, and Brendan has been with me for almost all of them, I believe. Chris Veskar, the CEO of Stavati Aerospace, and I made little short clips that come out of some of these interviews. And one of them is really important because it all is about Ken Shoulders. And Ken Shoulders and Chris Veskar were in a business relationship at Stavati to use all of Ken's charge cluster or EVO technology, essentially, right? So it's not a short, but it's a video, and it is the one. Keep going, Brendan. Actually, let's do that one. The EVO equals vacuum object equals charge cluster. That one, and then and these are really short, and then I'll show you one more.
I was saying in the other group there, the Model G group, that we have something in subquantum kinetics called an etherons, and they're the basic building blocks essentially. And I was saying that if we can make a connection between etherons, charge clusters, and ball lightning, because I think they're all pretty much one and the same, they're just fractals of the others. What do you think about that?
I think that's not such a bad idea. And he put in, I think, parallels to ball lightning and EVOs. I think he has papers about that. And so, the whole idea is of the ether again, is something that's very thought provoking and ties into some of his work. And, you also sort of want to look into Rupert Sheldrake, if you haven't already.
Yes.
And, he got into big trouble on TED by stating that the speed of light isn't really constant. And so that, he violated the golden rule of the establishment. So
I like
the
that.
rules need to change, and they are changing. That's the beautiful thing about it, right?
Yes.
And that was probably one of the greatest TED Talks ever. But
I love it.
And I think there's one more, Brendan, where he's talking about Ken Shoulders' work and how it relates to science in general. So it is, let's see, keep going.
Well, one point I want to make while you're looking there is that why don't we ask the question, when light goes from one medium to another, the following medium, why does light travel at the speed of light?
Yeah, it's like speed of light in a vacuum is what they're talking about. When the constancy in a vacuum is for the conventional.
I'm saying,
so
where does the energy come from to speed the light back up after it goes through a medium? Is what I'm saying.
Ooh, that's a good. Yeah, well, we know that it comes from the ether, basically, but but how to model that? That's a good point.
Right,
yeah?
Light is not emitted, right?
Yeah,
people think light is emitted, but it's not.
It's a perturbation.
Yes.
It's a compression and release. Yeah.
So light doesn't actually go from one place to another.
No,
it's not something that travels like a photon, right? The whole thing is all screwed up.
Yeah. Keep going, Brendan. Keep going. Keep going. It's going to come up here some point here. Keep going. There's a good one there about how Ken Shoulders foiled the patent office, but let's not look at that. There's also this one letter from Richard Feynman, but keep going, Brendan. There's a really great one here about nanobubbles from
You've been very busy
Moray.
with this.
Keep going. Yeah, I've been making lots of little ones. We're getting really, there it is, the pillar of the future of science. That's the one. And the one beside it is really cool too, because that's Pete Peterson. And when we started this, we didn't know that Pete
And
Peterson
so
and
not
Murray
only
King
do
knew
we
each other.
have had a full
Hi, Andy.
I was saying when we started all of this, we didn't know that Pete Peterson and Maury King knew each other. We found out actually right on camera, which was really cool. But this is Chris from one of the interviews.
Initiative, the engineering's been ongoing. And with respect to the Ken Shoulders technology, that is really viewed as one of the, I wouldn't say pillars, but almost the pillar of the future of science and our understanding of the cosmos. And so how we combine that with a variety of other electric universe ideas.
Yeah.
So, you have a situation where you're working on propulsion, but at the same time, you're trying to solve the mysteries of the universe. And they kind of go hand in hand, which is
they do, yeah.
And it's of course great to talk to people like you, Maury, who've been involved in all of this, and I've heard of you for years and years and years. So I'm glad to finally meet.
Yeah. I guess I could ask the key question, right? I think the key question is the technology for propulsion, inertialess drive. What I mean by that is you can do a hairpin turn and not feel the inertial stress of being slammed against the wall. You're controlling warping the space-time metric. Well, that's really the key. That's what the flying saucers and all the advanced technology have that under control. That's really the key. You're using, let's say, the 0-point energy or whatever science you want to use to warp the space-time or create artificial gravity. So, does your company do that?
That's one of the areas that we're exploring. Yes. And so all of, we're trying to continue Ken's work in more of a commercial sense, but it's kind of the same philosophy and
okay.
Yeah, cool. Yeah, so there's lots of good stuff on there. Shows a lot of the relationships and whatnot. And we'll be making more shorts, even out of some of these things that we've talked about, like I did last time too. So very cool.
Great. Yeah.
I was going to say something. I've forgotten what it is, so I'll just leave it.
Do we want to maybe shut the recording off so we can talk a little bit more candidly now?
Yeah. Okay. Well, thank you everyone for coming today, and I hope you have a wonderful rest of the day. Cheers. Bye.
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 Bye.